Hello guys, I'm Yash Khanolkar and today I'm going to demonstrate DLIC Experiment 7, which is for Schmitt trigger and its applications. Now, the first circuit which we will be seeing is the inverting Schmitt trigger. So, in an inverting Schmitt trigger, we have connected Vin to the inverting terminal of the op-amp. And this circuit is basically a comparator circuit, but the only difference is that we have connected a feedback loop right here through a voltage divider circuit to the non-inverting terminal of the op-amp. Now, the major flaw of the comparator circuit was that it was very prone to noise. But in the case of inverting Schmitt trigger, this circuit is immune to noise. So the output voltage we will get at the output is fed back to the input, and Vt can be either plus beta Vset or it can be minus beta Vset. So we have a calculation to find this, and we can take two values of R1 and R2, and we can take any values here. So we have taken 1.5k and 1k in our case, and we can pass it through this equation and multiply it by Vsat, which can be either be 14 volt or 15 volt, and we get 6 volts in our case. So the upper trip point and lower trip point are plus 6 volt and minus 6 volt respectively. So yes, so we directly go to simulation. So we check V in and we check V out. Yeah, so we can see that in this case we can take an example like Vt can be plus 6 volts, and in the first case Vt is greater than Vin, so we will get plus beta Vsat and we get Vsat at the output right here. So if Vt is less than Vin, now if Vin increases to greater than 6 volts, then the output drops to minus Vsat, and the feedback gives Vt as minus beta Vset. Now, even if the input drops here to below 6 volts, still we have minus 6 here, and this will be either 3 volt or 4 volt. So minus 6 minus 6 minus 3 or minus 4, it's still in the negative. So the output remains minus Vset. And now if we give Vin a negative value less than Vt, then this we will see a change of state right here, and it will return plus Vset. So this is all I can say about the inverting Schmitt trigger circuit. So the next circuit is the application of inverting Schmitt trigger, which is the astable multivibrator. So the astable multivibrator is also called as a square wave generator circuit, and it also has a voltage divider circuit right here, and it works on the charge stored at C1. So if C1 has a value of if the value of C1 is becomes greater than plus beta Vset, then we have a state change at Vout, and if it becomes less than minus beta Vset, then also we have a change of state at the output. So we can see this now. You can check V, and we can see that it is a freely running wave right here, and we can check V out, and we see that whenever we have a change from beta plus beta Vset to minus beta Vset in C1, then we have a change in output. So it goes from plus Vset to minus Vset. And this is all I can say about the astable multi-operator circuit. So the next circuit is astable multi-operator with Zener diode. So in this circuit, in the stable multivibrator circuit, you see that the output voltage is very much greater than the input voltage. So if we want to restrict the output voltage to a lower value, we used a stable multivibrator with Zener diode circuit. So yes, this is the circuit of a stable multivibrator with Zener diode. Yes, so the only difference here that we have two Zener diodes connected in inverting configuration to each other. So this Zener diode clamps the output voltage. The rest of the circuit is the same as the previous one, and we can simulate this now. We can see that V in is exactly the same as the previous circuit, and we see V out. We see that V out has got significantly reduced, and this is due to the clamping effect of the diode of the Zener diodes. And so the next application is a triangular wave generator. So this is what we call as a triangular wave generator. This is basically a stable multivibrator circuit, ahead of which we have connected an integrator circuit. So we know that if we the output which we get at the stable multivibrator is a square wave, and if we pass a square wave through an integrator, we get a ramp wave. And this is the output of the triangular wave generator. And we can see the simulation right here. Then we can check at VO. You can see a square wave at the output of the astable multivibrator, and we can see that we are getting a ramp at the output of the integrator. So in a triangular wave generator, we have the rise time as and fall time as equal. Now, if we want unequal rise time and fall time, we do a circuit called as a sawtooth wave generator. So we are going to the sawtooth wave generator now. Yes, so this is what we call as a sawtooth wave generator. The first part of the circuit is still the astable multivibrator, but the second part of the circuit is a little bit different. We are connecting a variable DC voltage right here at the non-inverting terminal of the op amp, and we have a very variable resistance right here. So we can change the value of the resistance to change the value of the non-inverting terminal, which changes the rise time and fall time of the output wave. So we are connecting this to the power supply VCC and VE, and we will see the simulation right now. So we can check again V out here, and we can see this is a square wave, and we check V out at the integrator, and we see that we are getting a sawtooth wave right here. This is because of this is because of the values of resistance R6 and R7 right here. If we change the value of the resistance, then the rise time and fall time will differ. So this is all I want to say about Schmitt trigger and its applications, and thanks for watching the video. Thank you.